An ordinary annuity is a financial instrument that we use to either save money while we are compounding that money, or we can use it to take a series of payments from a lump sum of money. An ordinary annuity is one type of annuity, and it, like all annuities, it consists of a series of equal payments. Equal payments meaning the dollar amount is the same for each payment or withdrawal, depending on how you're using the annuity. And it is a series of payments. These payments occur at regular intervals. It might be monthly, it might be semi-annually, or something else. In an ordinary annuity, the payments are made at the end of the payment period. In the diagram I'm showing here, it is a 4-year ordinary annuity, and the payments are coming at the end of each of these years. The ordinary annuity equation is shown here, where A is the future value of the annuity, R is the periodic payment, that's how much we put in every 6 months or 12 months or biweekly. I is the periodic interest rate, and it is in decimal form, and it's equal to the nominal interest rate, or oftentimes it's given as the annual interest rate, divided by M. M as in Mary, that's the number of compounding periods per year. Excuse me, 1 plus I is raised to the n power, where n is the total number of compounding periods over the life of the annuity. And n can be calculated by multiplying m, the number of compounding periods per year, times the number of years that the ordinary annuity is in existence. In the problem I'd like to show you, Devin has decided he wants to retire when he has saved $1 million. That's a good target figure. He's able to save $300 per month from his paycheck, and he places these funds in an ordinary annuity that pays a 6% annual rate of interest, and it's compounded monthly. We want to know the number of years that, there's a typo, Chris, Devin, whoever this person is, must save before retiring. All right, with all these problems, I start out by writing down what I know in terms of M, N, and I. M is our number of compounding periods per year, and we said we're compounding monthly, which means that we have 12 compounding periods per year. N is equal to M times the number of years. But we don't know the number of years. In fact, that's what we're trying to find out. But we do know what M is. M is 12. So we can write this equation like this. And this will be an important one, and we will return to that equation at the end of the problem. I is the periodic interest rate, and it's equal to the nominal interest rate divided by M. We have a nominal interest rate of 6%, and we're going to divide that by 12 total compounding periods. Compounding periods per year, giving us 0.5%. Now we can write our equation for our ordinary annuity. Let's see, $1 million, that is A. That's going to be our future value. So I'll just kind of abbreviate and write 1 million that way, is equal to R, the amount we place in our periodic payment, times the quantity 1 plus the periodic interest rate 0.5% or 0.005 raised to the n minus 1, all of that over that periodic interest rate. And now we want to simplify. Well, what's left here that's unknown? N is our only unknown, and that's where we are going to find the number of years. Okay, first thing I'm going to do is divide both sides by 300 and multiply by 0.005. I'm going do that in one big step here. So we have 1 million times 0.005 divided by 300 is equal to what will be left on this side. I'm going to combine the 0.005 and the 1. 1.005 raised to the n minus 1. And now, let's see, I'm going to add 1 to each side. And let's see, okay, I'll come up here and continue. 1 million times 0.005 divided by 300 plus 1 is equal to, what's left? 1.005 raised to the n power. Now I'm going to do some math, and I'm going to calculate what this value on the left-hand side is. Pull up my calculator. I've got 1 million, 3 more zeros. Do it right? Yes. Times 0.005 divided by 300. And that gives me 16.67. Now I'm going to add 1 to that, and we'll have 17.6 repeating. 17.6 repeating equals 1.005 raised to the n. Now I'm going to use one of the properties of logarithms that states if we take the natural log of both sides of this equation, natural log of 17.6, natural log of 1.005 raised to the n, when we do that, this exponent n can come down in front and be multiplied by the natural log of 1.005. n times the natural log of 1.005. And I still have log of 17.6 on this side. Now I'm going to divide both sides by the natural log of 1.005. And I'll put n over on the left-hand side. Let's see, natural log of 17.6 repeating divided by the natural log of 1.005. And now I'm going to pull my calculator back up, and we're going to calculate what this is. I need the natural log of 17.6. My Windows calculator works just fine. I'll take the natural log of that number, divide by 1.005, the natural log of that number. You can see up in the top row here, it shows you exactly what you're doing. Equals 575. 575. Is that enough accuracy for this problem? Oh, we'll put 0.8 on there. Probably should give them at least another decimal of accuracy there. All right, that is n. What is n? Well, we defined n in this problem as the total number of compounding periods, and since we're dealing with monthly compounding, this n is the number of months that Devin or Chris, take your pick, has to save in order to earn $1 million, putting away $300 a month for 6 years. Okay, so I'm going to shoot down over here. And let's say, okay, that is, well, we had an equation up here. N is 12 times the number of years. Or we could turn it around and say years is equal to, let's see, I'm going to divide both sides by 12. N over 12. Or 575.8 over 12. And what's that equal to? Divide that by 12. Should give us a number of years. 48 years. 48 years Devin has to save money in order to become a millionaire, earning 6% compounded monthly. Well, let's see. Let's hope Devin is fairly young because 48 years, if he's 20, now he'll be 68, and that sounds like a good time to retire as a millionaire. I hope this video has been helpful. Look for more.